Okay, let's get started. So, as compiler engineers, we spend a lot of time trying to optimize programs. So optimizing means measuring performances, but it seems that measuring performances is not always that easy. And I think Kristof will talk today about how to measure performances and what kind of problems we have to solve and what solutions we could have.
Solutions. Yeah, so as Arno said, probably as compiler engineers, even if you're not working on tuning code generation all the time, even then, from time to time, you're faced with a situation where you have to evaluate a patch or a particular commit and just evaluate, was this good for performance or bad for performance? Two typical use cases where you do this is, well, as a pre-commit test, while you're still developing your patch, you want to know, I'd like this patch to improve performance, does it actually do so? Or as a post-commit performance tracking, I think like the current commit rate to trunk is something like 100 commits per day. We need something that just tracks if nobody accidentally made a mistake somewhere. And we observe that quite often measurements give conflicting results, and also over time, bit by bit, we're realizing that every so often the answers may not be conflicting, but maybe even misleading. I'll give examples further on. So in the rest of the presentation, I'm assuming that you're doing benchmarking or measuring execution time on a system where you already went to some effort to optimize the setup so that you will not have too much noise coming from what I call CPU external events. For example, things we do is when we run a program, we pin it to one particular core on a multi-core machine, assuming that if there are interrupts and the machine needs to service something else, the operating scheduler will move it to other cores. We turn off all the daemons and processes that are not needed, and we make sure that CPU frequency scaling doesn't occur. So I try to think about like what are big categories of reasons why sometimes you get an unclear answer. Is this patch good or bad for performance? The categories I came up with are the following. So quite often on one benchmark you get an improvement, and on another benchmark you get a regression. So you don't have a clear black and white answer. Similarly, on one microarchitecture you get an improvement, on another microarchitecture you get a regression. A third category is a noisy system. You run the same program multiple times and you get slightly different performance results back. And then the fourth category is a chaotic system where you run the same program multiple times, you get the exact same number back, but then you change a program in a way that you think actually shouldn't make any difference to performance. Maybe you just link object files in a different order. You get a different result back. Okay. So I try to illustrate this with just a few charts. So here you see the vertically represents execution speeds, and there's two benchmarks. The circles represent the code generated by the original compiler, and the triangles represent the speed of the code generated by the compiler with your super duper optimizing patch. So as I said, sometimes, like in this example, sometimes on one benchmark it's an improvement, on another benchmark it's a regression. It's hard to make a conclusive decision on whether this is better or worse. With a noisy system, you might get something like this, where you just run the program multiple times and you get slight variations in speed. Now, on a chaotic system where, for example, you change link order, or there's something else going on where you have a slightly different program layout, you might find out that your conclusions gets reverted. Like instead of having a a faster program with your patch, now you have a slower program. So if you think about that, how should you really be measuring this? From a more or less scientific point of view, what you should be doing is you should try to measure the impact of programs across all possible program layout variations. And then you might get something like the gray circles and triangles on the chart, and then you can apply statistical analysis. And in this one, probably, like if you did proper statistical analysis, you might see like on benchmark 1, you get an improvement, and on benchmark 2, you get a regression. And still, you don't have a conclusive answer because the results are different across benchmarks. Anyway, for the rest of this presentation, I'm going to focus on, is there anything we can do to cope with noisy and chaotic systems better? Since I think the solutions to attack that problem are purely technical. I'm not going to focus further on deciding which benchmarks matter or which microarchitectures matter the most, because I think solutions are not purely technical. So just some characteristics of what we observe in a real system of noisy performance. So this is just a very brief summary of some slides I already presented in the San Jose meeting last year. So experiments I've done there is where I ran programs from the test suite on a big little Cortex-A53, Cortex-A57 system. So this is a system where on the same chip you've got a Cortex-A53 core and a Cortex-A57 core, which is nice for experiments like this because you know that lots of the parameters of the system are actually the same because the cores are inside the same chip. So so on these charts, what you see from left to right, all of these dots are just measured performance for a particular run. So all of these dots just show performance measured for multiple runs of the exact same binary. Luckily, most of the runs, they're relatively low noise. But then there are exceptions. Some of the runs have substantial amounts of noise. And one of the observations we've made is noise is not consistent between cores. It's not because on one core you see noisy behavior that you'll also see it on other cores. And just a third observation we've seen is that this noise isn't distributed in one particular way, so you can't assume normal distribution of noise. We've seen many different kinds of distributions of noise. So just a few characteristics of what we've observed noisy behavior looks like. So now moving on to some examples of chaotic behavior. For this, I first started just going through academic literature and see what people have observed before. So this publication by Raman and a whole bunch of other authors in 2009, what they did here is they took the Spec 2006 benchmarks and they changed linking orders. So just on your linker command line, you change the order of the object files, which makes that you get different program layouts in the resulting binary. So what they plotted here is something called a violin plot. Each figure there represents a single program executed multiple times with variations in the program layout. The violin, yeah, I'm calling it a violin. Each figure vertically, you could see it represents the distribution of execution times observed over these multiple runs. I'm assuming that the scale on the right-hand side is not readable, but it goes from -2% to +4%. So what they've seen is that on quite a few of these Spec 2006 programs, they see something like maybe 2% performance variance between just changing the order in which you link object files together. This was on a x86 machine. What they've also done is they've correlated the performance fluctuations they've seen with performance monitoring events, so coming from the performance counters, and they've concluded that for quite a few of the performance variations they've seen in these programs, they can with statistically significance conclude that this is coming from branch misprediction variation, sometimes from level 1 iCache variation, sometimes from level 2 cache miss variation. A second paper by Ovitz and others also uses the same technique to reorder the order in which object files are linked together. In these graphs, they what they try to do is they try to think like maybe like an engineer. They try to give an answer to the question: is Clang 03, does that produce better code than Clang 02? And then they evaluate over a number of program layouts, because if you want to do this statistically properly, you have to pick your samples from the whole space. And one of their famous conclusions there is there's no statistical difference between the speed of generated code between 02 and 03. This was at that point in time for Clang. Another thing they tried, which is the right-hand chart, is they just changed the size of the Unix environment in which the program ran. That has an impact on the location, on stack locations. So just the stack is shifted a bit. And they also observed that there they saw up to 10% performance variation in some programs. So it's not just code layout differences, data layout differences can also have an impact. And just the last of these academic publications that I'm going to talk about here. This is by Calavera in 2013. What they did is they thought, oh, maybe we can randomize a little bit more than just changing link order. What if we did an LTO compilation step and we reorder whole functions? So instead of reordering translation units, you order functions. In theory, you should get more randomization. It's hard to tell if they actually saw more randomization or not, but at least they also reproduced on the same benchmark sets back 2006 on a similar kind of x86 machine. They reproduced, yeah, we see more variation if we randomize program layout. So after reading all of this, I thought, well, this is all quite interesting. I want to see if I can reproduce some of this. So what did I do? After reading these articles, I thought, like, okay, could I go push the boundary a bit further even and try to randomize even more so that I've got a bit more confidence that I'm actually sampling from the space of all possible program layouts? The way I was thinking about this is, in the past I've observed that sometimes I wrote an optimization where I just changed one single instruction in the program. I just added one single instruction in the program, more or less in the cold part of the program. And then I observed, hey, there's a performance difference somewhere else. And obviously, it's not that one instruction that I added, so it's just a slight fluctuation in the code layout. So I thought, I actually want to randomize a bit more. Can I do it within the function also? I tried out two approaches. So basic blocks, some of the basic blocks end in an unconditional branch. If you can put some extra space after the unconditional branch. And at runtime, you will still execute the exact same trace of instructions. I also thought, can I push it even further a bit? And I also did a transformation where I made sure that all basic blocks end in an unconditional branch, which means that I am adding lots of extra branches to the program, but then I can randomize even more. So all of this was implemented as a machine function pass for AR64, and I ran the experiments across programs from the test suite, Spec 2000, and a number of all the benchmark suites we often run. In total, 479 programs. So what are the results of this? So in this chart, I'll explain it step by step. I also went for violin plots. So I did experiments with these 479 programs. Each of these programs are run 25 times. So it means like every violin plot represents something like 25 times 500 programs. It's like about 10,000 runs in every violin in every of those 6 figures in here. So the first one is where I did no randomization at all. The second one is where I didn't change programs at all, but just enabled address space layout randomization, so you get slight layout changes from that. The third one is where I did at random one NOP instruction after unconditional branches, basic blocks ending in an unconditional branch. But all of these 25 runs were done with the exact same binary. The next one, I produced 25 different binaries with NOPs inserted randomly in different locations. The fifth one is where, for every basic block, I made sure that it does end in an unconditional branch. So instead of just having fall-through basic blocks, there was always an explicit branch. So I can always insert NOPs between all different basic blocks. But once again, one binary, 25 runs with the same binary. And then the last one, 25 runs with 25 different binaries, so NOPs inserted in different locations. So what do we see here? So the 3 charts that end with no rand, staying for no randomization, the same binary is run 25 times. In there you see the figure on there. That's noise levels. You just run the same binary over and over. And the figure to the right of them is where you run the program with a different program layout. So you see that that shows you how much extra variation in execution time you get, which I would call it the effect of having chaotic behavior. So overall, you see like +9, +11, +20%. You might say that, well, the effect isn't that bad. The effect of noise on your variation in program execution time, that's like the main contributing factor. We don't have to think about this chaotic behavior too much. But I went and looked for, so what are the examples where I see quite a bit of variation, not coming from noise, but coming from this chaotic behavior. So on the top row, that represents bzip2 from Spec 2000s. By the way, this was run on Cortex A57. On the left-hand side is the noise levels you get, so not too much noise. And on the right-hand side, just with inserting NOPs after unconditional branches, you see like, oh, it's almost like bimodal behavior starts occurring. So this is, I'll read it out for you if it's not visible. So the standard deviation with chaotic, with the NOP randomization is 1.16% for bzip2. And then the bottom one is the biggest chaotic behavior I noticed from a program in the test suite. There I had standard deviation of almost 11%, which means like the bimodal behavior, there's 20% performance difference between those 2 runs. So even if you only see this chaotic behavior in a small percentage of all possible programs, it actually is painful because you're trying to evaluate your performance improving patch. Quite often when you're working on some tuning, you know that maybe 95% of the programs that will leave alone and 5% of the programs that will be a substantial improvement. But all of these chaotic or noisy runs, you will have to go and investigate why did it change performance. So it's So even if there's just a small number of programs giving misleading results, it still takes time to go and investigate. So this again is a screenshot that I also presented in San Jose about noisy systems. So this, by the way, this is a screenshot from LLVM's LNT Web UI. At the far right, this was just an example where we're tracking performance of a particular program. I think it's a program called Sim from the test suite. We noticed, oh yeah, all of a sudden you get bimodal behavior there, just noisiness. But now with this, these few insights around chaotic behavior, I'm starting to wonder, like, we also saw some jumps where we didn't see noisiness, but maybe they're caused by chaotic behavior, like a slight change was made in the program layout, and we drew the wrong conclusions at the time that this was a significant change. Maybe this isn't a significant change. So just a few more observations on the randomization I did. Just inserting this shows how performance changed rather than this plots the performance changes rather than the variation in performance. It just shows that if you insert the knobs after unconditional branches, your performance doesn't change on average. In individual programs, it might change. If you start introducing unconditional branches after every basic block, of course, your performance will change by about 10%. I also just double-checked because all of these papers from literature, they used Spec 2006, and they seem to see a bigger chaotic effect than what I was measuring. I didn't use Spec 2006 because that just runs for too long. I already took up our board farm for quite a long time, and people were starting to shout at me for how long I took up our board farm, so I just stuck to Spec 2000. But at least in Spec 2000, we see they're about 3 times less noisy than the average across all of the programs we run. And yeah, the chaotic behavior has like a bigger effect there. So I think the measurements I've done agree with the measurements that were done previously in the literature. So in summary, if you really, really correctly want to evaluate the performance effect of a patch, I think that you have to inject randomization. So you get samples from across the whole space of possible program layouts, and you have to do enough runs to get a statistically valid result. But then, isn't this going to be painfully slow? Right now, most of us don't do this. I hear everyone, whenever you need to do a performance evaluation, everyone complains about, oh, I don't get my results fast enough. So if we want to do it this statistically correct way, by doing an order of more runs, we're going to make life even an order more painful for ourselves. Is there something we can do here? So since I started reading some academic papers anyway, I thought, oh, let's go and see if they have some suggestions. So these are some of the papers I already talked about. Some of them are papers about doing microarchitectural evaluation, so from computer microarchitects. And there's one paper in there describing what people have done to do performance tracking of Mozilla Firefox over time. So I'm going to go through this pretty quickly. There's a number of techniques that have been proposed to avoid measurement bias, which is measurement bias, that's the thing that you get if you don't take into account the chaotic effects. So some people suggest you have to run across a wider range of benchmarks and many programs not to get misleading results. Quite a few suggest you should randomize program layouts. Also quite a few say, well, you should use confidence intervals so that you know that you can say 95% probability the actual effect is X percent. There's also a number of suggestions they made to increase running time. So one of the suggestions is actually try to estimate how many samples, how many runs you have to do to get a particular confidence intervals, so that you don't do too many runs, you only do the runs that are necessary. Some of them suggest, well, reduce the inputs of your program. And one of them suggests just do one run for every revision of top of trunk. This was the Firefox one where they tried to track performance of top of trunk. A very brief summary of what LNT, the test suite, does today. LNT, what the test suite supports external benchmarks. So you might say there's some functionality there to make it easier to run many different programs. Right now, there's functionality where if you submit a result to the server can say, I noticed that the result changed compared to a previous revision of the compiler. Maybe you should do some extra runs. But right now, the extra runs is a fixed number of 4 extra runs. So maybe it helps a little bit to get smaller confidence intervals, but probably this can be a bit smarter. The test suite also has a small mode, so to run on reduced input sets. Multi-revision analysis, while on both the daily report page and the run versus run comparisons, there's some support there to take into account data that you might have collected from different revisions of top of trunk. Multi-sampling, so like on one of the previous screenshots, you already see that the charts do show all of the measured results. LNT will run programs multiple times and collect all the data, but doesn't do that much of an analysis on it. And then around multiple revisions, one of the, a trick that was added recently is that on a daily, also a hash is calculated of the binary being produced, so that if you track the performance of a binary over time, LNT can know that, from one LLVM revision to the next, actually the binary didn't change. So if you see a difference in performance, you know it's just going to be noise. We found it actually pretty helpful in just quickly disregarding noisy results. So in summary, what are my thoughts on where probably we can spend a bit of effort to make life for us easier in improving LNT in the test suite. So I was thinking about 2 different use cases. One is where we have a post-commit bot tracking the performance of top of trunk. Ideally, that should give you feedback within an hour, so you don't have much time to do lots of advanced stuff. If the feedback you get is 6, 7, 8 hours, it means you only get feedback 1 day after you've made a commit. Ideally, you want to go for 1 hour. So there, I think it probably makes sense to improve the multi-revision analysis. In one of these papers, they talked about doing it with an exponential backoff, so the most recent results get a higher value. I think that's something to look into. For the test suites, so right now we have small input sets, but one of these papers also has a nice way to measure just how much you can reduce input sets without affecting the statistical, with a statistical method, so that you wouldn't change the conclusions you make. So maybe we can make the small input sets a lot smaller without affecting the validity of it. I'm thinking for the pre-commit runs where you're working on a patch and you want to get feedback back on how good it is, depending on how patient you are, maybe waiting for hours or even waiting for a few days on results is just about acceptable. Maybe that's where we have to do the randomization. Furthermore, in the test suite, we should be adding more benchmarks. I think that the current work on the CMA classification of the test suite actually helps a lot in adding benchmarks, and if any of these more advanced techniques we add, they just work out of the box for all of the other benchmarks you plug in. And probably we could also look into, so right now when we're in multi-sampling mode, you just say, I want 3 runs of every single program in the whole test suite. Probably you can get a big gain if you somehow figure out which programs are noisy or chaotic, run them more, and the ones that are very stable, run them fewer. So, just in summary, noisy and chaotic performance effects make our lives harder to come up with the right conclusions on, was a patch actually good for performance? I managed to randomize program layout with a pretty simple machine function pass which runs very late. It's not upstream, but if I hear interests, then I'm very happy to push it up for review. And I think with a few relatively simple further improvements to LNTN and test suite, we can probably already go a long way to cope with some of these noisy and chaotic effects without making performance evaluation an order of magnitude slower. And that was all. Thank you very much.
It's question time, so please proceed to the microphone if you have some.
To minimize the noise from the function layout, could you always apply some kind of profile-guided function layout optimization to minimize the noise when you add the other random stuff?
Sorry, I didn't get the first part of the question.
Can you reduce the noise by always applying profile-guided function layout optimizations?
You mean profile-guided optimizations that that optimize program layout?
Yes.
It's an experiment that has to be done. My gut feel is that it probably won't, because from looking at these numbers, the bimodal results you get, it seems to be coming from conflicts in data structures internal to structures internal to your core, where you, for example, have cache conflicts or branch predict conflicts in the tables. With the program layout optimization, you do typically what you're improving is spatial locality, putting the hot codes together. It seems like those are not strongly related, but once again, I'm not sure. It's an experiment that would have to be done. Yeah.
Yeah, actually my question was probably in a similar direction. So in my experience, these chaotic effects usually tend to have some underlying cause in the microarchitecture where you run into some effects in some cases and don't in others. So could you use these techniques to sort of try to pinpoint and identify which effect is causing a particular chaotic behavior by, like, for example, if you have this cloud of runs, identifying a very good and a very bad case to try to analyze?
Well, one of these papers that I pointed to from the academic literature, that's exactly what they did. So they used performance counters. So basically what they did is, yeah, just do a performance run, collect cycle count, collect branch misprediction, collect cache misses. So you've got tuples of this kinds of information for multiple runs with randomized layout. And then if you do an correlation analysis on that, you can decide if you've got, like, there's a correlation between, I don't know, cache misses and cycles. You know that very, very, very likely it's something related to the cache that's causing this effect, yeah. Myself, I haven't done a methodological way to do this, but I've done a few point experiments, and yeah, it pretty quickly shows up what is causing it, yeah.
So first, to answer your question about the PGO, you're changing how you benchmark the program. So you're actually benchmarking something different. And then, you know, even if that reduces the noise, it's now a different run. So you're not really benchmarking your O3, which everybody's going to use. You're benchmarking a very specific set of flags that nobody's going to run. And then you can get, like, into a local minimum that other people are never going to see. So that's one of the problems. So the perf results that you guys have?
Sorry?
The perf results, right,
yep,
that you guys have. You could use that. So whenever you have this bimodal thing, you could try to get the perf results and try to use that to see if there was like a cache miss or something, and then automatically flag, this seems to be the cache, because you already have all the information in the the profile runs.
Yeah, indeed. It's like the same answer to Ulrich. It was exactly it shouldn't be too hard to do that. Yeah, like right now, James is working on improving LNT so that If you happen to be running on a Linux system, it can also automatically for you collect Linux perf results, and with that data, probably we're not too far off to be able to do that analysis, yeah.
When I was at Sony, our test data was sort of generally very large games, and in particular, we found that micro benchmarks were particularly useless in terms of assessing the effect of optimizations, and it's really what we found particularly was it's really worth running the code cold with the caches uninitialized at least once, so you can get an idea of the cold code performance of the because that kind of in case of games, almost all code is run cold. There are a few hot spinny loops, but they're relatively few. Back in the days of Quake, for instance, you had a lot of hot spinny loops, but modern games tend to have very few. So it's worth having a mixture of tests in your test suite, which both do sort of loop type code and a lot of sort of load store call branch type code as well.
Yeah, absolutely.
Any other question? So let's thank again our speaker.
Thank you.